definition 1.18. The topological space X is Hausdorff if for every pair of distinct points x and y in X, there exist disjoint neighborhoods U and V of X and Y respectively. Okay. So this Hausdorff property is one of the separation properties. It says that X and Y are somehow separated from one another by neighborhoods. And, all right, let's try Munker's problem 17.13, which says, show that X is Hausdorff if and only if the diagonal delta of X is closed in X times X, which has the product topology from X. Okay. So this diagonal, it just consists of all ordered pairs where the first and second coordinate are both the same. Okay. And if you imagine that X is the real numbers, then if you sort of graph what the diagonal would be in that case, you can see why it's called the diagonal. Right? It would just be sort of the line y equals x that you've seen many a time. All right, well, to prove this if and only if statement, let's do a sequence of equivalences. And I can begin by saying that X is Hausdorff is equivalent to the definition, right? For every x1 and x2, I'll use x1 and x2 because they're both in X, which are distinct. There exist disjoint open sets U and V in X, right, with x1 in U and x2 in V. Good. That is equivalent to the following, right? If we have x1 and x2 in X, that's the same thing as having an ordered pair x1 comma x2 in X times X, right? And then just to assume that x1 and x2 are not equal to each other, that just means that this ordered pair is not in the diagonal of X, right? So in other words, this is in X times X minus the diagonal, or it's in the complement of the diagonal. Okay. So for every such thing, just copying our previous statement now, there exist, well, having open sets U and V, like we do, is going to be the same thing as having a basis element U times V for the product topology on X times X. And then having x1 in U and x2 in V is the same thing as having the point x1, x2 be in U times V. And then I claim, well, certainly U times V is in X times X, since U and V are both subsets of X. I claim that having U and V be disjoint, right, that means that the intersection is empty, right? That means they have no overlap. And so in particular, claim that U times V doesn't intersect the diagonal anywhere, right? Because if it did, it would have a point inside with where the two coordinates are the same, and then that point, the coordinate x would be in both U and V, okay? Contradicting the assumption that U and V are disjoint. So I have that U times V is actually in the complement of the diagonal. Okay. Good. So you can double check and convince yourself that what we've written here is equivalent to what we had up here. All right. Now, that is equivalent to this complement of the diagonal being open in the product topology on X times X. Okay. Why is that? Well, how do you show something's open? You take some point, x1, x2 in it, right, which is depicted in our picture here as this point, and you have to find some basis element of your topology, in this case the product topology on x times x, which contains that point x1, x2, and is contained in the thing that you're trying to show is open, right? That's exactly what we have in this statement here. And, well, you see what it looks like, right? It's this base element u times v. Just the product of u down here and v up here. All right. Well, the complement of the diagonal being open is, of course, equivalent to the diagonal itself being closed in that same product space. All right. So we're done. We've shown that X is Hausdorff if and only if its diagonal is closed in the product x times x.